Hello, dear friends. Let's look at exponential functions introduction, and maybe hopefully we'll go to logarithmic functions also. So let's deal with exponential functions. What is an exponential function? Exponential function is when the unknown quantity is in the exponent. So the unknown quantity is usually represented as x, and that x is the exponent here. So that's the reason why it is called an exponential function as far as I can understand. So let's look at this particular 2 to the x here. Normally, an exponential function is written as f of x equals a times b to the x. So we'll see first an example and come back to this general form. So I have in Desmos entered this equation ready for you. So this is the tabular form of 2 to the x. So 2 to the x, if you see all of these points here, you have several points here. Let me mute this off. So you have several points here, right? So all of these, if you see, if you substitute x values and the negative values into x, you will have the curve very close to the x-axis, right? But it never has a negative value. So you have to remember that. So all of these points actually go to only the positive y values. And if you also observe, even if we give a very low value for x, like suppose negative 100, even then the y value is positive. Because when you bring down the exponent into the denominator, the value of y is still positive, but it has a very low, very small value of y. And hence, it looks like the curve is actually touching the x-axis, but it never does. And on the other side, if you actually look at the positive values of x, you will see that from here on, the values of y are increasing. It starts small, but slowly it gives into very big numbers, big values for y. You will see that in the table very easily. So 8, 16, 32, because we are actually doubling them, isn't it? So in a real life situation, it's just like the COVID cases right now. You're starting small. It started very small with just one man, right? And then it soon spread to so many other people, and so it grew exponentially. That's the word that they use, like this is what it really means, because the graph is actually increasing exponentially. So that's the graph. And also, if you see this line that the curve seemingly tries to touch but never does in reality is called the asymptote, isn't it? So let's go more into the details of the graph. So this is 2 to the x, and we have just seen this is the y-axis, x-axis, and we also saw that the graph cuts here at this is the y-intercept 0, 1, right? Why? Because 2 to the power of 0, if you substitute 0 here, 2 to the power of 0 is 1. So the y-intercept is always 0, 1. I don't say always, but always only when there is no number in the front. Suppose you have something like 3 times 2 to the x, then the y-intercept will not be 0, 1. It would be 0, 3, because 2 to the power of 0 is 1, but there is 3 in the front. So 3 becomes the y-intercept. And hence, this a here that we are talking about, it is also giving a y-intercept value. So this is called a stretch factor for this function, or the initial value, if you go and look into the application problems of this. But this a is in reality, a y-intercept with respect to the graph. So I may not be perfect in drawing the graph, but this is how it looks like. This is the exponential function. And what if it is a half here? By the way, this is the asymptote, and that being the x-axis, and the equation of x-axis is y equals 0. If you have half as the base, a fraction, this base should always be positive, by the way. So if you have half, now let's look at the graph if the base is half. So this is the graph when you have half to the x. So half to the x actually makes the graph decrease. The y values are decreasing as you go from left to right side on the graph. So for small values of x, the value of y is really big, right? If you take -3 here, for example, the value is 8, so and so on and so forth. And it comes down as the x value is increasing. And it's so much so that it almost feels like it touches the y-axis. So it is the other side, on the other side. So this is like actually the value of y is decreasing, and hence we call it decay function. So this is an exponential decay. This is the decay, and this is the growth function. And this is how the graph looks like. You would still have the y-intercept as 0, 1, and the graph seemingly touches the y-axis. So this is, again, y equals 0 will be the asymptote. All right. So in both cases, if you see, the domain of the function is all the x values which are spreading out on the negative side and the positive side. So the domain would be all real numbers. Okay, we'll see more about that in just a bit. So here, for example, this function, this is a growth function because the values of y are increasing as you go from left to right side of the x-axis. So this is a growth function. And the domain of this function is all real numbers. So you would say x such that x is all real numbers, or you can just say x belongs to all real numbers. And in interval notation, it will be -infinity to infinity. And the range is going from 0 and above, from 0 through infinity, right? But it's not touching the 0 though. So you would just say y is greater than 0, or in interval notation, you would say 0, comma infinity, both open intervals, right? And we have seen that the y-intercept here, because there is no number in front, it's just 0, 1. Asymptote is the x-axis, which is y is 0. So the graph is actually increasing from left to right, isn't it? So from all the negative values of x through the positive values of x. So the increasing interval is -infinity to +infinity. Okay, and the graph is not decreasing, so there is no interval for decreasing. But if you actually look at the ends of the graph, as x approaches to the negative side, right? As x approaches -infinity, what is happening to y? Y is actually approaching 0. Y is going to 0. And as x is approaching to the positive side, y is actually going to the positive side of infinity. The y values are increasing exponentially. So this is the end behavior. If you see the the decay function, this is the decay. In the decay function, the domain is still the same. All these still remain the same, -infinity to infinity. The range is also from 0 through infinity. The y-intercept is the same. The asymptote is the same. But the function is not increasing, it is decreasing. So the function is decreasing from -infinity to +infinity. And the end behavior, as x approaches -infinity, the y is actually increasing here. So y, or the f of x, you can use f of x also here. Both mean the same. F of x approaches +infinity. Oops, this has its own mind. Sorry about that. +infinity. And as x approaches +infinity, f of x, or the y, approaches 0. Okay, it's the opposite way of writing the other one. Okay, so let's look at something on the Desmos to get introduced to the inverse function of exponential functions. So suppose I actually switch all these points on the original graph. I'll make all the x as y values and y values as x. And when I do that, this is what I see. So I have everything ready. So it's just clicking on So I'm just reversing or switching the x and y values, right? And I'm doing that because I'm making y same as x on the y equals x line, right? So if I do that, then you will see that even for small values of x, small positive values of x actually, you'll have the y values very small and closer to the y-axis, right? So if you actually join all these dots here, if you join all these dots, you will see that the curve is actually passing through these points and it's actually making a curve, right? So this curve is our inverse curve of the original exponential function. So the exponential function has its inverse, or its, how should I say, the symmetric curve as the log function. So this is called the logarithmic function. So how would I really write it as an equation? So here logarithmic functions are defined as f of x equals log to the base b of some value x. So we'll actually go into the details of what actually logarithmic functions mean in a little bit or in some other video. But for now, we'll just say that f of x is log to the base b of x. So b is the base of the function. And in the combination that we have just taken in this example, here the original function, exponential function, was 2 to the x. So if we have to convert that, we will write that the base is always the base, so it will be log to the base 2 of x, right? So if we actually put that into the Desmos graph here, that's the curve. So that is log base 2 of x, and it passes through the points which have been switched, where the x values, x and y values have been switched. So this is the log function for y'all. And the log function, if you see, is not going below 0 on the x values, but on the y values, it takes all values of y, negatives and positives. So if you see that the domain and ranges have been switched also because they're inverse functions. So log functions and exponential functions are actually inverses to each other. So the domain of the log function is actually x greater than 0, and range would be all real numbers. So let's write that down quickly. We'll take this as an example. The domain here is x such that x is greater than 0, or in interval notation 0 infinity. And the range is all real numbers. So this time you would say y belongs to all real numbers, and also negative infinity to infinity. The x-intercept is actually, this is the x-intercept, 1 and 0. And the asymptote this time is the y-axis, and the equation of y-axis is x equal to 0. And the graph is actually increasing from 0 through infinity. It's not going below 0, isn't it? So the graph is increasing from 0 through infinity, open interval, and it is not decreasing. And there is a catch here when you write the end behavior here. So we cannot say as x approaches negative infinity. There is no point of writing that because the graph is not going to negative infinity, but is actually approaching 0. As x approaches 0, f of x is approaching negative infinity. And as x approaches positive infinity, f of x also approaches positive infinity. Okay, so this is the these are the features of log functions, and we will actually know what is a logarithm in my next video. Okay, the practical applications of log functions. How do we actually see that as a conceptual thing? Okay, thank you for watching. I'll see you next time.